Here we're looking at node voltage analysis. If we take a circuit, let's say that circuit there, if we were to try and analyze that using series and parallel resistor analysis, we'd very quickly discover that we can't break that circuit down any more than it already is. There's no series resistors that we can simplify and no parallel resistors that we can simplify. So how do we analyze this? What if we were looking to find, for instance, the voltage at this point? Or what if we were trying to find the current through this resistor? How do we go about that? Node voltage analysis uses Kirchhoff's current law. There's a number of steps. Our first step is we pick a reference node. Now in this circuit, the reference node is obviously the ground. Now by nodes we're referring to junctions, and there are only 4 junctions in this circuit. Here's a junction, here's a junction, here's a junction, and here is a junction. And we're going to select the bottom junction as our reference node. Sometimes you can easily see which one to pick. In this case, if we use this one as the reference, the other 3 we can label them with voltages relative to ground. So our second step is to name every node except for the reference. So this is node 1, node 2 and node 3, or you could say junction 1, junction 2 and junction 3. So we name these nodes and we give them voltage labels V1, V2 and V3. So these are the node voltages. Now any resistor, the voltage across any component in this circuit can be identified by these voltages. So in the case of say R5 or R4, then the voltage across R5 there is simply V2, because it's got V2 at the top, 0 at the bottom, so the voltage across it is V2. If we're looking at one of these resistors, then the voltage across that one could be considered V1 minus V2, or it could be considered as V2 minus V1, depending on which way we're looking at it. So we've named every node and we've labelled these ones with voltages. Now we're going to use Kirchhoff's current law at each node, because Kirchhoff's current law says the sum of the currents into or out of the node equals 0. Now the reason we put voltages there is because we use Ohm's law, and for instance the current in R4 is V1 divided by R4. So let's create an equation that represents the current at the node. Now we draw all the currents as leaving the node. The blue current is V1 over R4. The green current is V1 minus V2 over R2. And the red current is V1 minus V3 over R1. So this current here is this voltage minus this voltage divided by the resistance. This current here is this voltage minus this voltage, that's the voltage across here, divided by this resistance, gives us the current. Now we draw all the currents as leaving the nodes. So when you do this, draw currents leaving the node. That helps you work out what happens when you have a current source instead of a voltage source. If we're dealing with node 1, then we've got V1, we've got V1 minus something, V1 minus something. So when we're dealing with V1, node 1, it's always first in the equations. If we're dealing with node 2, then it would be first in its equations. Now, if we had a current source, just imagine this circuit exists where we've got a current source here. This arrow, we're drawing the current as leaving, it's pointing the same direction as the current source. So we would add it, because the arrow we drew was the current leaving the node, and that current source is leaving the node. so we add it. If we were calculating this node, then the current's coming into the node, which is the opposite direction to the way we draw our arrows, so it would be subtracted. Okay, back to our original circuit. So let's do a Kirchhoff's current law for each node. So node 1 is the top equation we've already looked at. Node 2, V2 minus V1 over R2, V2 over R5, V2 minus V3 over R3. V2 minus V3 over R3. So V2 comes first in this node 2 equations. Now V3, we can't work out the current here because it's a voltage source. Here we're working out the current because it's a voltage divided by a resistance. Here we don't know. But V3 equals Vs. Now in this equation it looks like we've got three unknowns, V1, V2 and V3. But it turns out that we do know V3. So there's two unknowns and two unknowns. Two equations, two unknowns. So we're going to solve these using Gaussian elimination. Let's give this circuit some values. So we've got a supply voltage of 20 volts. This is 20 volts. Top resistor, 20 ohms. 15 ohms, 10 ohms, 5 ohms, 5 ohms. So we simplify this first equation. V1 over 5, V1 minus V2 on 15, V1 minus 20 on 20. That's 20 volts and that's 20 ohms. Equals 0. So we simplify this down until we get to this equation here, where we've brought all the V1 terms together and all the V2 terms together. We do the same for equation 2. We put all the numbers in. We start simplifying. We simplify until we end up with all the V2 terms together, all the V1 terms together. So we're going to solve these two equations. So here's equation 1, here's equation 2. Now because this V2 is something over 60, let's change this V2 to something over 60. So we've multiplied top and bottom by 4. So that we can eliminate V2, we've multiplied the top equation by 5.5, the whole equation, every term. So the 19V1 becomes 104.5 V1 over 60, minus 22 V2 over 60 equals 5.5. Now we're going to add the top equation and the bottom equation. So we add those two equations together and the V2 term will disappear, because in the top equation it's minus 22 V2 over 60 and in the bottom equation it's plus 22 V2 over 60. So when we add them together it disappears. So we end up with 100.5 V1 over 60 equals 7.5. We solve that and we get a voltage for V1. We substitute that into either equation, doesn't matter. Here we've substituted into equation 1 and we've got a voltage for V2. So let's put those voltages on our drawing. 6.27 volts, 4.48 volts. So does this seem realistic? Does it feel right? Well, let's just have a little rule of thumb test. Let's ignore all these values in here and just look at 20 volts through 20 ohms and 5 ohms in series. Let's just consider that. So there's 25 ohms around there. 5 ohms is a fifth of 25. A fifth of 20 volts is 4 volts. So if there was none of this circuit here, this would be 4 volts. So 4.48 seems within the ballpark. Let's ignore all the outer circuit and just look at these two resistors here. 10 and 5 in series. 5 is a third of 15. 10 plus 5 is 15. That's a third. A third of 20 volts would be 6.67. So that seems like it could be within the ballpark. So 6.67 and 4 here, and we stick a resistor between them. That would drag this one down, that would drag this one up. That seems reasonable. Is there any way we can actually check it's correct? Well, if we take that resistor out, we could actually now look at that and consider that a power supply and analyze it using a Thevenin or Norton equivalency. So if we built a Thevenin equivalent, if we analyse that, found the short circuit current, and it turns out the short circuit current would be 1.3636 amps. If we found the open circuit voltage, it would turn out to be 13.0435 volts. And if we found the internal resistance, or the Thevenin equivalent resistance, it would be 9.5655 ohms. So you might want to pause the video and write those numbers down. Then if we stick the 5 ohms back on, so in the circuit at the bottom, if we had 13 volts there and an internal resistance of 9.5655 ohms, and we stick a 5 ohm there, and we solve for the voltage across the 5 ohm, it turns out to be 4.4776 volts, which is the voltage, approximately the voltage we had for V1 originally. So our node voltage analysis looks like it's giving us the right answers.